Okay, can you see the lecture slides? I'm talking to you. Can you see the lecture slides?
Yes, please.
Yes.
So why are you quiet?
Yes, please.
Okay, so we are going to now take some
Yes, please.
examples on probability. We've already gone through some of the definitions that we need to know as far as this course is concerned. So let us take some examples to illustrate those definitions that we have gone through in our previous lectures. Now let's take this example. So here we are conducting a study on 100,000 white people in South Africa. And we found that 45,000 of them have blood type O. And our interest is to estimate the probability of having blood type O. So the number of people with blood type O, they are 45,000. The total population, that is the total number of white is 100,000. Then the probability of having blood type O is equals to the number of people with blood type O divided by the total population of white people. This is just an assumption. So what that means is that we are going to have, this is supposed to be 45,000, not 44. 45,000 divided by 100,000, and that will give us 45%. So the probability that you are going to get a patient out of 100 people to have blood type O Hello, can you hear me?
Yes,
Yes.
I think the network,
Yes, sir.
I think there was a network problem. So let's move on. So here is the example that we were looking at. So the probability of having blood type O out of 100,000 people, that is the white South Africa, is 45%. So the probability of having blood type O is 45. Let's look at another example. We have the number of positive amoebiasis infections to be 59. And the number of negative infections is 151. We want to find the probability of having the infection. And then we want to also find the probability that you do not have the infection or one does not have the infection. So from the information that has been given, the number of people with infection, so I'm using A to represent the event that you have an infection. So the number of people with infection is represented by this, and that is equal to 59. The number of people without infection, so I'm using A complement to represent those who do not have the infection. So the probability that one does not have the infection, the number of people who do not have the infection is 151. And then that means the total number is going to be 210. So the probability of having the infection is going to be equal to the number of infected cases divided by that of the total number. And that is going to be 59 divided by 210. That is going to give you 28%. So the probability that you test someone and the person has infection is 28%. So there is low chance of infection, which is 28%. Now let's look at the other way around. The probability that you have no infection. The probability that one does not have an infection. So if we know the probability that one has infection, the probability that one does not have the infection is 1 minus the probability that one has an infection. So the probability that one does not have the disease is equal to 1 minus the probability that one has the disease. One has the disease, and that is 1 minus 0.28, and that is going to give us 72%. The other way you can compute this is that we know that the number of people who do not have the disease is 151. So we take 151 and divide by 210, and then we'll get 72. So the probability of someone not having the disease is very high, which is 72%. Now, this is another example. Let's look at 100 newborn babies in a maternity of Sunyani Municipal Hospital. So let's say there are 100 newborn babies in Sunyani Municipality Hospital. And out of the 100 newborn babies, we have 55 of them to be females, and then we have 45 of them to be males. Now, we want to calculate and interpret the probability that newborn baby is a female, and also calculate the probability that the newborn baby is not a female. So what do we do here? So we know the number of people who are males to be 55. So if we want to get the probability that the newborn baby is a male, is a female, we divide the 55 females by 100, and that will give us 55%. So there is 55% chance that a baby born out of 100 babies in the Sunyani Municipal Hospital is going to be 55%. That there is that chance. And then for the males, you take 45 divided by 100, and that will give you the probability that a newborn baby is a male. And that is that. If you don't want to do that, once you compute the probability of being a female, then you subtract that from 1 to get the probability of not being a female. Now let's move on to conditional probabilities. Conditional probabilities. So you can see in the previous probabilities, we are just computing the probability without talking of condition on anything. So here we want to say that the probabilities that we are going to estimate depend on certain information. So here we are saying that let us consider 2 events, A and B. And the probability, if we want to compute a probability of B given A, then that should be written as probability of B given A. The other way you can say it is that given that A has already occurred, given that event A has already occurred, what is the probability of B also occurring? the probability of B given A. If A has already occurred, what is the probability that B is also going to occur? And how is this expressed? We can express this conditional probability as probability of event A occurring intersection probability of event B occurring. Divide that by probability of A. This is how we express the conditional probability. Provided the denominator, which is the probability of event A occurring, is not equal to 0. If the denominator is equal to 0, then this function will be undefined. Now let's consider a situation. Under this situation, you know the deck of cards. The deck of cards consists of 55. So we have the diamond, we have the club, we have the spade. Each of them, there are 4 sets, and each set consists of 13. So 4 times 13, we get 55. So the deck of cards, we have 55 of them. But we want to find the probability that we have found a card, and that card is a king of the clubs, given that there are clubs in the 52 deck of cards. And this can easily be expressed as probability of king of clubs divided by intersection clubs. Divide that by probability of clubs. Now we are finding king of clubs, intersection clubs. So what this simply means is that we are looking for the king of clubs. And then we divide that by probability of clubs. So now there is only one king of clubs out of the 52 deck of cards. So what that means is that we are going to have 1 over 52. That is the probability of king of club. Divide that by probability of clubs. How many clubs do we have? We have 13 of them. So we take 13 divided by 52. Then if we work this out, so we are going to have 1 over 52 multiplied by 52 divided by 13. And that will give us, so 52 will cancel 52, leaving 1 over 13. And that is what we have here. So the probability of finding a king of clubs, given that there are clubs in the deck of cards, is 1 over 13. Now let's take another example. Suppose that you have been given a problem and you are able to formulate your probabilities out.
Please, sir, your audio is not coming.
The audio is not coming, eh?
Yes, please.
What do you mean by my audio is not coming? Is it that you cannot hear?
Yes.
But you can hear now. Can you hear me? Hello?
Yes, sir.
Can you hear me now?
Yes, sir.
So suppose we have 2 events, A and B. And these 2 events belong to the sample space. And we know that the probability of event A is 0.6. And the probability of event B is 0.2. Probability of event A occurring, given that event B has already occurred, is 0.5. Now, we want to find A, probability of event B occurring, given that the event A has already occurred. B, probability of event A occurring or event B occurring is the same thing as when you say probability of A union B. Then we find probability of A not occurring. So what is the probability that event A will not occur and event B will occur? Then the D, we want to find the probability of event B occurring, given that event A has not occurred. Now, but we know that probability of A given B is equals to probability of A intersection B divided by probability of B. We know probability of A given B to be equals to 0.5 here. So we substitute it. We know also probability of B, which is here, to be equals to 0.2. Also come and substitute your 0.2. So this will imply that 0.5, which is the probability of A given B, equals to probability of A intersection B. Divide that by probability of B, which is 0.2. So you make the probability of A intersection B the subject. And that is just going to be equals to 0.2 multiplied by 0.5. And that is going to give us 0.1. Now let's answer our problem. The A. Probability of B given A. This is the same thing as probability of B intersection A. Note that probability of B intersection A is the same thing as probability of A intersection B. So whichever direction is correct. So probability of A intersection B divided by probability of A. We know our intersection to be this, which is 0.1. And we know our probability of A to be 0.6. So we substitute them. 0.1 divided by 0.6, and that will give us 0.17. So we have 17%. So the probability of event B occurring, given that event A has already occurred, is 17%. Let's look at the second one. We want to find the probability of event A or event B occurring. In other words, the probability of A union is equals to the probability of A plus probability of B minus probability of A intersection B. We know the value of probability of A, which is 0.6, so we substitute it. We know the value for probability of B, which is 0.2, we substitute that. And we know the intersection to be equals to 0.1, so we substitute that. And if we solve that, we are going to get 0.7, that is 70%. So the probability of either the event A or event B occurring is 70%. High chance of any of the events to occur. Now let's look at C. C, we want to find the probability of event A not occurring and event B occurring, or probability of event A not occurring but B will occur. Event A will not occur but event B will occur. What is that probability? But remember the law of total probability. Theorem 2, probability of B is equal to the intersection of probability of A, is equal to the probability of the intersection of A and B plus the probability of event A will not occur, but B will occur. We are looking for this component here, this guy. Okay, we are looking for this guy here. So what do? We make that the subject. If we are making this the subject, this will remain here, and then we take this one to the other side of the equal sign. So we are going to end up with probability that event A will not occur, but B will occur, to be equal to probability of B minus probability of A intersection B. We know the probability of B to be 0.2, so that is what we have here. Then we know the probability of A intersection B to be 0.1, which is here. So if you subtract that, you get 0.1. So the probability that event A will occur, but B, the event A will not occur, but B will occur. You see that the probability is very low. Now, when we computed the probability that either event A will occur, you see the chance was very high. So if you are finding probability that one of them will occur and the other will not occur too, you won't get it to be high, it will be low. So the chance that one of them will occur and the other one will not occur is very low. The chance that any of them can occur is very high, that is 70%. And the chance that one of them will occur and the other event will not occur is just 10%. Let's look at the final one. The final one is saying that what is the probability of event B occurring given that event A has not occurred? So if event A has not occurred, then what is the probability that B is going to occur? So you can see that in this situation, which even before we compute the probability, we should know that we are going to get a low probability. This is because once one of the event has occurred, there is high chance the other one will also occur. Either of the event occurring, that is the union. Probability of event A occurring or event B occurring is very high, 70%. So if you are finding the probability that A has not occurred, you have information that A has not occurred. What is the probability that B is going to occur? You expect a very low probability because what we have here is that they all have higher chance to occur, which is 70%. So once one has not occurred, the chance that the other one is going to occur is going to be low. So here, we express the probability of B occurring given that the event A has already occurred to be equals to probability of B intersection A. That is the probability that B will occur but A will not occur. Divide that by probability that event A will not occur. Remember this probability here. So we know this probability. We know the probability that B will occur, but A will not occur. We know this value, and that value is 0.1. But we know the probability that A will not occur. This guy here, we can express it as what? 1 minus the probability that this event is going to occur. So we have probability that B will occur, but A will not occur to be divided by 1 minus the probability that event A will occur. And if we do that, we are going to have 0.1, divide that by 1 minus 0.5, and we are going to end up with 0.25. So the probability that event B will occur, given that the event A has not occurred, is 25%. So you can see that very low, and that was expected. And this is how you solve them. What you have to note here is that in real life situation, you are not going to be giving probabilities value just like I have given out here. These probability values are taken out of a question. So the question will be in terms of words, sentences, which you have to then extract the probabilities values from them, and then you do your calculation. So of course, in real life situation, you won't be getting these values here, but there will be a problem which you will extract your probability values from. Any question? Any question? Any question? Obed. Also, your hand is up, Jeffy.
Yeah, yes, sir. So please, can you go over the NB? Yes, sir. Please, can you go over the notes, the NB. Can you go over that, please?
Which part?
The NB before after the example for the NB.
What is NB?
Note that probability of A.
Yeah.
Yes, please.
Yeah, so what do you say? What is it that you don't understand here?
So please, can you go over?
What is it that you don't understand here? Hello?
Yes, sir.
What is it that you don't understand under notes?
we were able to get the probability of A intersection B divided probability of
But you,
B.
but you know how this component here is expressed from the conditional probability.
Yes, please.
So what
Yeah.
is it that you can, is it that you can substitute the values and make the probability intersection the subject, or?
I can.
So what is your problem?
I wanted you to go over it again.
No, but if you have problem, then you tell me. But if you don't have problem, this is what you are looking for: probability of A intersection, probability of A given B. This is what you are looking for. But you already know that it is expressed as this from the conditional probabilities in the previous slide. You know that. You know that from this slide, isn't it? Look at it here. Yeah.
Yes.
So if you come here and someone is now talking about this, why should you be dragging us back? Yeah, so just tell us what is it that you don't understand here, then we easily show it. Because going over, I may not say what you didn't understand. So just tell me, this is where I don't understand. Hello?
Yes, sir.
Yeah, just tell the class, I got to this point, I don't know how you have done it. Then we rectify that, then we move on.
How we were able to get, you see, a probability of A intersection, probability of A divided by B is equal to probability of
Where is
A
probability
intersection.
of A divided by B?
This place, probability of A.
Go on.
Yeah, probability of A slash probability of B.
Where I can't see where you are reading because we don't have. Yeah, so
Hey,
probability of A
this
slash
one
probability of B, yes.
Sir, please, we can't hear you.
Go on, probability of A slash probability of B.
B is equal to probability of
Sir.
A intersection B divided by probability of B equals to 0.5. Like, I don't really understand how we have the 0.5.
So 0.5G, what is the value of probability of A given B? What value is
It's
given for what value is given for probability of A given B?
0.5.
So why is it that you don't understand where we got the 0.5?
Oh, okay.
We have provided
Then,
information for you here. You are using that information to solve your problem. Why are you saying you don't know where we got 0.5? You don't know where we got this 0.5 from.
I've now seen it.
Okay, so let's move on.
Thank you.
Okay, so that we are done. Any other question on this slide before we move to the next one?
No, sir.
All right, so let's move to the next slide. So just like I said, it is not always the case that people will just provide you these figures for you to do your computation. In the next slide, we are going to look at a problem, and then we'll learn how to extract the events from them, then also to formulate the probabilities from them. So let's go to the next slide. So in the next slide, we are looking at a situation of transistors. And then we are saying that we have a container that contains 5 defective transistors. And we are saying that that transistor, we are saying it is defective because that transistor, they do not last for 2 months when you put them into use. And then we have 10 transistors that are partially defective. That is, they use for some hours and then they stop working. And then we have 25 transistors that are acceptable, they are good. Now you decide to choose a transistor at random from the container and put it into use. If it does not fail immediately, what is the probability that it is acceptable? So you can see what is the conditional statement in this question. Can someone point out the conditional statement in this question? Can someone point out the conditional statement in this question? So you can see that they are saying that a transistor is chosen at random from the container or from the bin and put into use. And what follows is that if it does not fail immediately, if it does not fail immediately. If it does not fail or immediately fail, what is the probability that it is acceptable? So here, when you come, what you have to first do is that you have to formulate your probabilities. So here you are going to say that let A be the event that the transistor is acceptable. So A is the event that the transistor is acceptable. And then we say that let D, okay, let D be the event that the transistor is defective. So if we have, or in other words, if we use D, so we just say that let D be the event that the transistor is not acceptable. So if it is acceptable, A. If it is not acceptable, we put D. So we are saying that since transistor did not immediately fail, we know that it is not one of the 5 defective. So if it did not immediately fail, it is not defective. So the conditional probability, what we are interested in is here. If it does not fail immediately, so the transistor does not fail immediately, that means it is not defective. So if it is not defective, then we say D bar, it is not defective. What is the probability that it is acceptable? So you can see that we have this component here. The probability that it is acceptable, given that it is not defective. If it is defective, we just say D. If it is not defective, we say D bar. So what is the probability that it is acceptable, given that it does not fail immediately? And this is going to be equal to probability of acceptable intersection it does not fail immediately, that is, it is not defective, divided by probability that it is not defective. Now, you can see that if you have probability of accepting a transistor, intersection a transistor is not defective, it's just the same thing as saying probability of acceptable transistors divided by probability of transistors that are not defective. Then how do we do that? Add all the transistors. So the number of transistors that are acceptable is 25. So we have transistors that are acceptable to be 25. And the transistors, so if we take the 25 and then we take 5 and then 10 and add to that, so the total number of transistors is going to be 40. So the probability of acceptable transistors is going to be 25 divided by 40. Now, what is the probability of, what is the number of transistors that are not defective? So the first one, the 5 transistors are defective. So that means we have to take the 5 away from the rest of the transistors. So we are going to be left with 35 transistors that are not defective. So the transistors that are not defective, what is that probability? So the probability that a transistor is not defective is 35 divided by 40. So 40 will cancel 40, and then we simplify our probability. So the probability that you randomly selected a transistor and it does not fail immediately, the probability that a transistor chosen at random is 71%. In other words, the probability of accepting a transistor, given that the transistor is not defective, is equals to 71%. Isaac.
Say we are confused.
Yeah, point to where you got lost so that we explain, we take you along.
Say this question.
What is it that you have, I mean, you don't understand, so that we explain and move on?
Say, like how you are.
So just look
say,
at
like,
something
how-
here in this question. The number of acceptable transistors are how many? How many transistors are acceptable?
25.
25. What is the total number of transistors?
40.
40.
Okay, so look at something. Are you listening?
Yes.
So you can see that the defective transistors that are defective, they are how many? They are 5, isn't it?
Yes.
Can you see the whiteboard?
Yes, sir.
Yeah, I can see.
Yes, sir.
Transistors that are defective, they are 5, isn't it?
Yes, sir.
And then those that are acceptable transistors, they are equal to what? 25, right?
25.
Yes, sir.
And then we have those that are not defective. Okay, so we have those that fail immediately when put into use. So those that fail immediately that put into use, they are not effective. So this is equals to
10.
okay. Now, then we want to find the probability of a transistor being acceptable, given that it is not effective. Is that not what we want to find? Isn't it?
Yes, sir.
What we want to find. And you know how this one is expressed. And we are saying that if a transistor is not acceptable, because this one is expressed as, this one is expressed as probability of A intersection not defective divided by probability of not defective, isn't it? This is that, isn't it? Now this guy here is just the same thing as saying that the transistor is acceptable. So the probability of transistor acceptable is just the same thing as the 25 that we have here. Can you see that?
Yes, sir.
So that means this guy here is going to be probability A divided by probability of not effective. Now, so probability of so finding probability that a transistor is acceptable, that means if we add all this, we're going to get 40, isn't it?
Yes, sir.
Yes. If we add everything, we're going to get 40. So now if I want to find probability of acceptable, it's going to be 25 over 40.
Yes.
So I'll put that here. I'll put that on this one. So this is going to be 25 over 40. Now, the probability that the transistor is not defective. So if a transistor is not defective, it means that it's going to be this one together with what? The acceptable transistors. Can you see that? If a transistor is not defective, if a transistor is not defective, what that means is that it's going to be those that you put into use and they are used for some hours, together with those that are acceptable. All those transistors are not defective, isn't it? The acceptable transistors together with those that are not defective, all of them are the acceptable transistors together with those that you put into use and they use for some time before they stop working. All that together, that part is by, and that was why we did that. Can you see the slides?
No, sir.
No, sir.
Okay, I think the sharing has gone. Can you see the slides now?
Yes, please.
Okay. So if you do that, you are going to get 71%. And that is that.
Yes.
Now let's look at another one which is called the being. Okay, so I think we have to end the lecture here. The time is up. Oppo, your hand is up. Oppo, your hand is up. Can you please ask your question? Hello? Hello? Hello?